Welcome back. We named carboxylic acids and their derivatives. Now we're going to learn all the reactions of these functional groups. So let's start with a review. I think you remember oxidative cleavage of an alkene gave you aldehydes and ketones, right? But when you have something more oxidized like an alkyne, you can also oxidatively cleave that, but you're going to get the more oxidized products as well. So you're going to end up with the carboxylic acids. Potentially, okay, or ketones. All right, so that's one way to do this, and we are familiar with using ozone for that. So ozone followed by water workup will give us these carboxylic acids. Oxidation of primary alcohols. This carbon here is only bonded to one other carbon, so this is a primary alcohol. And this is sodium dichromate and acid, although sometimes you also see chromium trioxide in acid. That's another reagent that sometimes we throw them all under Jones reagent, but it's good for you to recognize these. You might get the actual formulas on exams in the future, or at other institutions or other exams you get. So anyways, primary is susceptible to oxidation fully to the carboxylic acid. If you want to stop it at an aldehyde, do you guys remember what reagent you have to use then? You would have to use a more mild reagent like pyridinium chlorochromate. Also has chromium in it, but it's got pyridine. It's a different oxidizing strength. Okay, so more mild. All right. And then this last one is anytime you have an R group with at least one hydrogen on it, that can get oxidized to carboxylic acid as well. So this R group, we call it oxidative cleavage of a benzylic position. So basically, we're keeping that carbon, we're cleaving everything else and oxidizing it. So we keep that carbon. The benzylic position is susceptible to oxidation. And you can imagine it has something to do with that position. Benzylic position is the one that's in resonance or has resonance delocalization with this pi system. That one is susceptible for oxidation. All right. Okay, so using those reactions and also a couple of other reactions you might like to know is when you have a nitrile. I'm pretty sure you didn't cover this, maybe a little bit last quarter, not sure. When you have a nitrile, you can hydrolyze it to a carboxylic acid. So that's good to know, okay, and we'll learn the mechanism for that soon. And then here, CO2 looks like this, and this is a lab that I like to do with dry ice. I think some of you remember this, trying to make that Grignard reaction. So this R group attacks this carbon, and then we make a carboxylic acid that way. So that's a very useful reaction specific to CO2, but very useful if you're looking for making a carboxylic acid out of a Grignard. There's the beginning of this reaction. I would maybe draw it from that. So let's draw the mechanism for this reaction. You can draw the ionic form of the Grignard if you like. It's not totally ionic, but it works. Okay, so just like that, and then you have the R group attached. Then you have the carboxylate, which then acid workup gives you the protonated carboxylic acid. Okay, so there's the reaction there. So let's practice maybe using some of these reactions, and I'll do A together, and you can check the answer key for the rest. Ethanol looks like this. We want to transform it to acetic acid, which is ethanoic acid, 2 carbons. All right, so we're taking a primary alcohol, oxidizing it all the way to carboxylic acid. You guys can write sodium dichromate or Jones reagent if you want, H+. All right, so or chromium trioxide, anything like that, or even KMNO4. Sometimes you see KMNO4 used for this. So, and we don't usually specify temperature in that case. We just say KMNO4 when you're just using it to oxidize alcohols. Okay, and let's try one more together. Okay, how about B? We'll take toluene, which is methylbenzene, and we want to convert it to benzoic acid, which looks like this. So 1 carbon carboxylic acid off a benzene ring. All right, and I think you know from looking above the reactions we just did, talked about oxidizing the benzylic position. So what you need are, we talked about that right here, Jones reagent or the dichromate ion, or KMNO4 also. In fact, I see this often with KMNO4, but you can use sodium dichromate or Jones reagent if you prefer. You know, a strong oxidizer and will work. Okay? I urge you to go through and review and practice these. And so try these when you can on your own. Okay? All right, now these carboxylic acid derivatives, how do they react? We just spent a little bit of time on how to make carboxylic acids. Let's now talk about how to start with a carboxylic acid or derivative of carboxylic acid. Again, what I mean by derivative are all of these functional groups, not the aldehyde ketone, but these other ones. These are the derivatives of carboxylic acids. All right, well, first let's understand a little bit about what makes these carboxylic acid derivatives different from each other. Okay, so first, if we take an acid chloride, for example, and we can look at it as having resonance contribution to some extent, but maybe not a lot, because that, you know, we always prefer the neutral form, but also we put a positive charge on an electronegative chlorine. Doesn't really love that. And over here we do the same thing if we had an NH2 group instead of a Cl. We could do the same kind of analysis. Now, this is interesting because this is just what the book says. It says this is not a significant contributor, but this one is. And you might wonder to yourself, well, why? Why would this be okay and that not? I mean, they basically look the same. The difference is in the nitrogen versus the chlorine, though. So these are some guiding questions here, maybe to think about in why there's a difference here. The more electron withdrawing group, if you remember from Chem 262, second quarter, remember electrophilic addition reactions? You had these benzene rings and you were adding groups to them, and some of them were electron withdrawing groups and some of them were electron donating groups. So I think you remember that chlorine was just weakly donating because it had lone pairs. It could weakly donate those lone pairs. But it didn't want to because it would make this positive charge on chlorine. So instead, we thought of chlorine and other halogens as slightly withdrawing, and that explained why they were slightly deactivators, okay? Slight deactivators. So we think of chlorine maybe a little bit more like an electron withdrawing group at times, although it is an orthopara director, so it does have that donating ability too. Nitrogen, here, I think almost always thought of it as a donating group because of its basicity. So that lone pair is able to donate itself more so than with the chlorine. So based on this answer, so we normally thought of this as an electron donating group, whereas with the chlorine, thought of it as an electron withdrawing group. So it would withdraw electrons toward itself. So the nitrogen, being more basic, allows for this resonance structure to be more significant. So it lends its electron density more. Is this consistent with the behavior that acid chloride does not have a significance contributor, but amide does? So hopefully approaching it with that idea of donating group versus withdrawing group can help you figure out that this resonance structure is more significant. We usually think of an amide bond like this. We usually think of that amide bond as partially pi, with a partial pi character to it. Whereas with the acid chloride, we don't usually think of it this way very much at all. So it has to do with that donating and withdrawing ability. So based on that, you can sort of come up with the reactivity, where we have the amide being the strongest donator group with this nitrogen. So we have the most resonance stabilization, making this weakest. Okay, so this is the least reactive carbonyl, because you have this partial positive of the carbon is actually stabilized by some of the electrons coming in from the nitrogen. And over here with the chloride, you don't have that so much. The chloride doesn't want to donate. So this partial positive stays nice and positive, very reactive. And so we see a trend that this oxygen here tends to donate in as well. So that's a little bit more reactive, but not as much. Remember, when this donates in, we create a positive charge. Oxygen's more electronegative, so it really hates positive charge. Just threw these in here. These are also reactive. They're sort of in the middle, though. But they don't always apply because there's separate reactions for aldehydes and ketones, and some reactions just for the carboxylic acid derivatives. So they're in parentheses, but we definitely know aldehydes are more reactive than ketones, so that's shown here. Let's skip over to this acid anhydride now. You see that there's some resonance here, but how would this be different from this ester? Well, some of you might see that we can also have resonance this way, and so that weakens the resonance going in one direction. See, so by trying to stabilize both carbons, you have less stabilization overall because you're sort of split between the two carbons. Okay, but you have a greater area in which you're stabilized, but these tend to be more reactive compounds, actually, and that's partially why is it's got to spread its charge both ways, and it doesn't do as good a job as going one way. All right, so what I'd like you to try to burn in your memory is sort of this pattern. Acid chlorides, most reactive with anhydrides, very reactive, these two. And on the other end of it, the amides and esters, less reactive. Now, do you guys notice where's carboxylic acid in all this? Well, carboxylic acid is a little bit different. It has the different character that we'll talk about and why it's not on here. Okay, acyl substitution wise, we learned about addition elimination. So I think you can figure this out. Nucleophilic acyl addition followed by elimination. So if I do this first, and usually we just want to do a couple of arrows at a time, not too many arrows. Don't go too crazy all at once. It's hard to follow that way. We get a tetrahedral intermediate. And then I think you guys know how to get from there to the end. We had just done the addition, so now we do the elimination. Now we could kick out the other group nucleophile, but that will be a reverse reaction. And it depends on how strong this nucleophile is, whether it's reversible or not. Usually if it's pretty strong, it drives forward. Okay, so this Z competes with the nucleophile in terms of coming back to attack. If Z is stronger, it'll come back and we'll go backwards. All right, so in general, to drive this reaction forward, we want to have a weaker Z than the nucleophile. So we want a weaker base that's formed, right? And that's what makes a good leaving group. So back to first quarter concepts. Okay, weaker base is a better nucleophile. Or sorry, weaker base is a good leaving group. All right, so notice that acyl substitution means we're going from a carbonyl to a carbonyl, but we're just changing this group that's attached. So that means we can go from, this acid anhydride, we could just change the group attached to this carbonyl and change it into an ester, or change the ester into an amide. But notice it tends to go this way because this is more reactive, so they're more susceptible for changing. So acid chlorides can go to anhydrides, can go to esters, can go to amides, rather than amides can turn into esters, can turn into, so it's sort of like fighting upstream if you go the direction of this arrow. This is fighting upstream, or going up the stairs, okay? So it's much easier going the other way due to reactivity. It's a reactivity series. Okay, so which is a better leaving group and which is a weaker base? Another way to think of that. Chloride is a weaker base, right? Its acid, HCl, is much stronger than the acid of NH3, which is ammonium ion. This is about pK of 10. This is about pK of 0. So much, much stronger acid, so much weaker base. So that means that as a leaving group, Cl- is perfect. It's a great leaving group, really stable on its own, not very likely to come back and displace the nucleophile. So that's why chloride is excellent leaving group, and that's why this is so reactive. Chloride is happy to leave, make place for somebody else. Whereas the amide, this guy, if you look at this, This is an NR2 with a negative charge. Wow, that's a really strong base. This is like sodium amide. Remember this in OChem 2, very strong base, stronger than hydroxide. So very bad leaving group, very poor leaving group. All right, so that explains the reactivity as well. If this reacted and got rid of a very strong base, that base would come back, right? And we'd still have this compound. So not as reactive as something that wants to change. So that's how this makes sense. Why would the anhydride, why would this part of the molecule be okay leaving? Do you guys see? This would be a minus charge, and then you would have resonance stabilization of this carboxyl part right here. So that makes that a good leaving group, which is why this is also reactive toward substitution. But esters, ester, the leaving group would be OR minus. Not so great, really strong base. So not as strong as amide, but pretty strong, like hydroxide. Okay, so these tend to be unreactive because their leaving groups are strong bases. All right, so acid chlorides, because chloride is a pretty good leaving group, these are pretty reactive. They're ready to get displaced. Okay, so practice identifying what's your nucleophile. Your reaction will be from nucleophile to the carbonyl carbon, and then addition and then elimination of the chloride. We'll do one of these together. Excess LAH, usually I think of LAH as a hydride, so that's my nucleophile. Now, for our purposes, we don't have to show a mechanism. If I showed a mechanism, I would stop here, draw the intermediate, show more arrows. But for our purpose, I think we just want to show the product. So I'm just going to combine my arrows. And that's sort of a no-no in organic chemistry. I think my professor told me many times, don't do that. You get bad habits that way. But as long as you know the difference, I think it's a faster way of getting to the answer. So we're not showing a mechanism, just a product. Then they say it's excess, so that's a big hint that we need to probably react it again. So here's another hydride, and I'm going to react it again. All right, so my final product is going to be, here's my two hydrides that became hydrogens, and acid workup gives me this water workup gives me this protonated oxygen alcohol. Okay, go ahead and identify what the nucleophile is. There's a couple ones that you might have trouble with. This one in particular, sometimes it's referred to as diol. H is one kind of reagent like this. Basically, it's like lithium aluminum hydride, but with only one H available. So instead of excess hydride, you only have one equivalent of hydride, one equivalent of H minus. Okay. Another thing is, so that's when you see something like this, and then this guy is a Gilman reagent, which I covered a little bit at the end of last unit. Basically, think of the ethyl group as the nucleophile. You just pick one of them, and that will be the nucleophile, like a Grignard reagent. Other than that, yeah, see if you can understand two equivalents there. And pyridine is just a non-nucleophilic base, so it's just the base that you have in solution as your solvent, and it looks like this but doesn't attack. It's not nucleophilic because it's bulky. All right, go ahead and give these a try and we'll check our answers. Okay, everyone, for this one, this is a Grignard reaction, so excess again implying that you need to use more than one equivalent. So that phenyl comes in, and I'm just sort of picturing it as the nucleophile, doing an addition and then an elimination. I get the carbonyl, but then I have it attack again. So I end up with two phenols, and then the carbonyl oxygen turns into a single bond, and then with an O minus charge it gets protonated. All right, for the next one, one equivalent here, so you just reduce it once, and then you have ethyl magnesium bromide come in, and that's going to attack here and make your ethyl group here, and then you protonate that oxygen. Okay, all right, so down here, this is a Gilman reagent. If you haven't used it, think of it like a Grignard, but it's a softer version of a Grignard. Since we talked about it, you know, if this had a conjugated system like this, it would attack at the 1,4 position, but it doesn't have that. So without that option, it will attack here. And so we do the addition, the elimination, and you get the carbonyl group here with an ethyl attached. And then you can reduce it using LAH, and then water work up to make it neutral. The next one is oxygen. Here is the weak base. This acid chloride's very reactive though, so it's happy to take that on. And then this eliminates. And I abbreviated the benzene ring as a phenyl group, so pH is fine. But notice that there's this pyridine, and the purpose of that is to neutralize this hydrogen. Someone has to take that off. You could use another one of these if you want, but the solvent is plentiful and really good at doing that. So it helps to have that solvent if it's slightly basic. And then this is the same exact thing. You know, you just attack there, and two equivalents because this in itself is a base. This in itself can deprotonate. So what I've shown here is that this will be positive, just like above with this example. And then we have another one of these solvent molecules come in. Solvent in this case is the reactant. And you just have that. So that's why we have two equivalents. My answer key says only one reacts, but that's not true. We have one reacting as a proton acceptor, just simply as a base to neutralize this. But that's why it's specified in that case. You might have thought maybe it reacted twice, and the reason why it doesn't do that is because that's, I think, where my answer key said amide is not very reactive. This is not very strong base, and an amide is not very reactive, so I will not have two of these attacking a carbonyl. So that's why I said that in the answer key. So the second one is actually just used as a base.